topological thing. So usually it's not a simple thing, but one thing which probably everybody knows already in this audience is the algebraization of the category of two-dimensional cobordism. So two-dimensional cobordism for me this is a category which has as object one-dimensional closed manifold, which there is only one of them, it's a circle. And so given, for example, a few of those, so monoidal structure in this category is given by disjoint union of circles. So you consider morphism of this category, it will be two-dimensional cobordism, which is surface. So this will be morphism which goes from 1 to 3. So this is one circle to 3 circles. And actually, so what is distinguished about this category is that this is so-called pro-category. So what does it mean that it's pro-category? It means that the set of objects is isomorphic to the set of natural numbers. This is what I will use all the time in the talk. In the way that the monoidal structure corresponds to the summation of the natural numbers. So this is, you see, so basically here there is just one fundamental object which is just 1, and every other object is 1 plus 1 plus 1, and you get 3. So this is why it is called a pro-category, and we study such things usually by looking at functors from this category to the category of the vector spaces. And this functor, which we call usually T of T, basically completely determined by assigning one vector space to this fundamental object, which is 1 in this category. So you just need to say where your functor maps this circle S1, and you know basically everything. And then to 3 circles, this functor will associate e to the power 3. And you ask if this assignment is compatible with the gluing. So that the gluing on that side corresponds to composition of this linear maps on that side. So this is what we usually call the QFT. And so what is also a very known kind of folklore theorem that all these two-dimensional QFTs are in one-to-one correspondence with so-called commutative Frobenius algebras. So meaning that this one vector space here, it should not come just alone, it should come with some family of kind of structure morphism. So you need a multiplication on this, so which is a map from V tangent square to V. You need a unit for this multiplication, which is a map from K to V. You need a co-multiplication. And you need a co-unit, which is a map from V to... And so I will, in the whole talk, I will use the notation. So with the colors, I'm not sure. I will try to be consistent, but I don't know. But so I will denote this multiplication. It's a map from 2 to 1. So the most difficult thing here is to know how you read your map. So I will try to consistently read them from bottom to top. But again, this is not given. Then K is a map from nobody, which is a dot to V. This is a map from 1 to 2. And this is a map from V to nobody. So this is my notation for these maps. And then, so Frobenius algebra basically means that this is an associative algebra with respect to this. You have the axiom, and it's also co-associative with respect to that. And you have one additional property which looks like, so basically, how do you compute this guy? And you compute this guy either by first co-multiplying and then multiplying, or you do this on the other side. So this is the called Frobenius axiom. This is what you require this guy to satisfy. And the theorem says, okay, so any commutative Frobenius algebra of this way, so commutative, by the way, meaning just if you multiply again, so this should be red here. This is what is being commutative on this picture. So this theorem tells you any commutative Frobenius algebra gives rise to such a functor. And moreover, even, you can see the whole, so you can characterize the whole category 2-cop in algebraic terms by saying that 2-cop is just a symmetric monoidal category generated by a commutative Frobenius algebra object who is S1 in 2-cop. So this is for me, this is the algebraization statement. So you replace something which is a priori topological to something which is completely algebraic, generated by one object which satisfies some structural property. Okay, and so the goal of this talk would be to push this idea that you can actually algebraize much more than just 2-cop in low-dimensional topology, and so the thing to algebraize is clearly 3-cop. So now, so the problem with 3-cop a priori is it's not a pro category. So usually when you're speaking about 3-cops, the objects are surfaces, and you have surfaces of genus 1, surfaces of genus 2, and you have 4. And then you have different union of those. So it's, you cannot put it into correspondence with natural numbers. However, it's enough just to modify a little bit the monoidal structure. So if you take the old monoidal structure like in 2-cop case, then this is not pro, but there is a well-known substitute. So we know in the 90s how to solve this problem, and then you just consider connected three-dimensional cobordism, and you replace your monoidal structure by something which is connected sum. So now your surfaces will supposed to have a boundary. So my surface will look like this. So it's a disk with some handles attached. So this is, for example, genus 2 surface. And now if I have another surface, so my monoidal structure will produce, so we'll do the same, we'll do the following. So this is just connected sum. So I have, on each surface, I have some distinguished interval, and I'm just gluing them along this interval, and I'm doing this, and this is already correspond to summation of natural numbers. So if this is 2, this is 1, then this is 3. So this is a category, this is what we want, because we would like to have one object and property of this one object which completely characterize some topological category. And so this structure was, I think, first it was Cranieta who were working with the structure, and basically, so what their observation was is that the object S1 is the object 1. So 1 in this case, it's a torus. It's a punctured torus, so with one boundary component, so with a disk removed. So this object, so this was observation of theorem by Cranieta, that this object in 3-cop is a Hopf algebra, is a braided Hopf algebra. Okay, let me call this braided Hopf algebra H. And so who is a braided Hopf algebra? So let me just recall you quickly. This is again an algebra, so it has a multiplication and unit. It's a co-algebra, it has a co-multiplication co-unit. In addition, it has a morphism, which is an antipode, which is an invertible endomorphism of H, which I will denote again, if I will think about by this, and with minus sign is the inverse of this guy, so it's a morphism from H to H. And that's it. And they satisfy all the properties except for this one, which is in white over there. So there's no Frobenius axiom. So this Frobenius axiom is replaced by Hopf axiom, which tells you again how you compute this guy. So you have multiplies and you co-multiply. It's morphism for h squared. And this morphism, how you compute it, so you take the first input, you co-multiply, you take the second input, you again co-multiply. And now, if you consider Hopf algebra in vector, you would just permute these two guys and then multiply again. But we are working, so this is an object, this is H, is an object in 3-corp. And 3-corp doesn't have a natural permutation, it has a braided structure. So you need to use this braided structure to permute these two guys, which I will denote graphically like this. And so this is the additional axiom which you will have in the case of Hopf algebra. Okay? And so I think you got my handouts here, and on the handouts, I think on the second page, now look, I know look quickly. On the second page, you see pictures. So this row of pictures, which present you structure morphism in the category of three-dimensional morphism. So the first one is the identity morphism, which you interpreted in the following way. So I think it was drawn like this. So they're all drawn like this. So this is morphism from 1 to 1. And again, so perhaps you use another color. So do you see this blue? So how do I understand this morphism? So this just means that you remove from the, so basically this is just a two-dimensional slice of a three-dimensional cube. So you have a three-dimensional cube. So a priori it's a morphism from a disk to genus 1 surface without a disk. But now what you're doing, you're removing a tubular neighborhood of this blue tangle. And this produces your morphism from a surface of genus 1 to surface of genus 1, which is the identity morphism. Okay, and perhaps I draw another one, which is a morphism from 2. So here we have 2, and here it will be 1. And this is a morphism which is correspond to multiplication, and it looks like this. So again, so the source surface, it's a surface which is this disk with this two small neighborhood of this attaching point removed, and the cube along this blue component removed. So this gives you genus 1 surface here, and genus 2 surface there, and this is a morphism from. And in this way,
this is already Crane and Yetter. In my mind, it was Gwenaël and Habiro or something like that.
It was Habiro will pick up on that. But I think the first statement is this hopeful, I think it was in the 90s. And then yeah, so you're Habiro worked on this. Kerla worked on this a lot. Lubashenko worked on this. And then Gwenaël joined also, and I also joined, so, and a lot of people. Asaida.
Like this.
Yeah.
Are your cobordisms embedded in R4 here, or are they just?
No, this one, yes, they're embedded, but this is exactly, thank you for your question. This is a great question, so I'm just immediately, so again, so you see, so my spirit, so I would like to see something like this, that 3-corp is a braided monoidal category generated by this one object, yeah, so I would like to see something like this. And clearly, so all the structure morphisms which correspond to these guys, they're all embedded in R3. So this is exactly why you need more than that. So you need some additional structure morphism on this Hopf algebra, and this will be integral, co-integral, morphism, and copairing. So let me draw these guys as well. So I think they've drawn.
Sorry, very quickly. So even if you don't embed, you still don't have a symmetric braiding here. It's just you just have a braided structure.
No, this is a braided.
Right. So it's not a symmetric hop.
It's not symmetric, and the braiding is given here. This is a braiding.
Thanks.
Okay. Okay, so let me, so basically, for my purposes, it is not enough to have this morphism, but if I will go for even more, so it will be lambda, which Evelina called always. So again, this is one, it's just a monoidal unit. I will just call it one, yeah? It's not the object one, it's not this one is H. Okay, so this is monoidal unit, so this is K in vector. Okay. So this is, which is called integral, then, so this is supposed to be a small lambda, and this is supposed to be big lambda, which is the opposite one, which is a co-integral, which I'm not allowed to call co-integral, it's called.
I gave up on that, so you can call them integral and co-integral because Ronald
I waited 2 years for that. Thank you. Okay, then how? So this is ribbon morphism. This is morphism from H to H, and the comparing, which from tensor unit it goes to H tensor H. And so now completely inconsistent with what was before. So let me add the pictures. So lambda, it's from H to nobody. The co-integral, it's the opposite guy. This is just with some number. So this is even morphism. This is kind of multiplication by real element if you from quantum group. So this is just morphism from H to H, and here's a number 1 tells you how many times I multiply. It's also invertible guy. So it could be plus minus 1, so I can go with integers. And this is guy look like this. So this form omega looks like this. So it goes from nobody to tensor H, okay? And they all satisfy properties. And the properties are drawn in the first, I'm sorry, which I'm taking, so I did go my slides. So you see here, so they satisfy, so first of all, so I'm not drawing here the standard Hopf algebra axiom, which is associativity, co-associativity, blah, blah, blah. And I'm just drawing the additional one, which correspond to this additional structure corresponding to integral, co-integral, and these guys. And so these are the additional properties. Okay? And then this object, so this H, with all the structure and satisfying the axiom in the handouts, so this object H is called общая hypercollinear algebra. So H with this M, eta, delta, epsilon, S, and tau, omega, so all the structure plus axioms. This is called общая hypercollinear. So then this is the first name there, and this is the last name there. So this is общая hypercollinear Hopf algebra. Because they were the first guys who introduced this with all this property. And so what we proved actually in our joint paper is that this category 3 Kopf, which is a pro category, so perhaps one can note it like this, so to distinguish with the standard 3 Kopf, so the one with this, which is pro, which is connected sum as a monoidal structure, is actually equivalent to the category of, so which we call 3 Alge. And this is a braided monoidal category, which is again pro. Category generated by BP Hopf algebra. And just to the sorry, Habiro. So here Habiro is coming, yeah? It's okay, draw it?
Sure.
Okay, so here Habiro Hopf algebra, yeah. So exactly, so we will see in a minute how this Habiro Hopf algebra depends. So basically I can tell you already, and this is just a portion of this one, of this BP Hopf algebra. And actually, so this was conjectured by something similar, so not exactly this, but it was first conjectured by Kerler. So Kerler was also, I think, the first using this word algebraisation. So he conjectured some basically this structure together with some set of axioms, but his axioms were not complete. And then Habiro added one more axiom to his set and claimed it as a theorem and announced this as a theorem, but never published the proof. And so he announced this, I think, in 2003 or something. So I think, I don't know, perhaps he's still working. But so in our setting, this theorem was actually a corollary of something more general, saying that, so this is what I call BBP. And so this was in the same paper corollary of something which was proven by Evelina and Ricardo separately in 2011. I think this is 25 or 24, depending on which version do you take. And the theorem says that there is a category of four-dimensional cobordism, which I call 4HB for four-dimensional handled bodies. So there is a four-dimensional category, which is actually equivalent to some algebraic gadget, which I'll call 4LG, so 4ALG, which is actually, again, a braided monoidal category generated by VP Hopf algebra. Okay, and you can pass, so the path between these things we describe in some work with Marco De Renci, where we also produce a lot of examples of this BP Hopf algebra. So you may ask, does it exist so is it easy to construct BP Hopf algebra given this huge set of axioms it should satisfy? And actually, there are a lot of BP Hopf algebras. So basically, what we proved, so any quantum group is one, at least produce you one, and any given C a braided monoidal category. Sorry, it's Riemann. So Riemann category. So for any Riemann category. So it may be simple or semi-simple or not, so as you wish. So for any such categories, there is a functor from this 4HB to this category, which actually sends this generating object, which in this case it's, so perhaps I should define this category first. This is possible, so just I wanted to first produce the full picture and to define the categories. So the object 1 in this category, it's not a torus, it's a solid torus. And so this solid torus is sent to end of this. So this is a categorical end of C, which any Riemann category. So it exists for any Riemann category, finite Riemann category. And so this produces you a braided monoidal factor between this 4HB and any Riemann category. So basically, any Riemann category produces such examples. And the second point is that, unfortunately, if this Riemann category is factorizable, so factorizable means that Hopf pairing is invertible. So in my notation, it means that if I take my Hopf pairing and apply integral on one side, not matter which one, I'm getting co-integral. So in Kirby diagrams, which I'll come soon, so it basically means that there is no difference between one and two handles. And so basically this means that the functor which we get in this case was a factorizable it's to this even category, it's factorizes through the boundary of this four-dimensional two-handled body. And then it goes there. So this basically means that the invariance doesn't see four-dimensional topology. They see just the boundary. So remember also the whole story of Richtich-Turayef invariant and three-dimensional topology. It's a story about modular category which are by definition factorizable. And so in this setting, somehow to be factorizable is not so a nice property. So it's better not to be. If you like to catch something four-dimensional, then factorizable is perhaps not what you would like to do. Okay. So I think at this point I would like you to just to define who is 4HB and who is okay. This is basically defined, but who are the four-dimensional handle bodies?
Sorry, what is the Habiro of algebra again?
Thank you. Exactly. This is what I wanted to say. This is a quotient. This is a quotient of this BP by this relation. So it's basically factorizable BP whole. We produce three. Yeah, and there is another one. Yeah.
Homological, yeah.
This is it's basically makes of something four-dimensional, something three-dimensional. Yeah, so it's exactly so. If this is a condition where this functor factorizes through that one. So yeah. Okay, thank you. That you're keeping attention. Okay. So who is a 4HB? So 4HB, it's again a pro category. So all categories I'm speaking here are pro categories. So again, you associate objects with natural numbers. So what are objects here? They are three-dimensional, one-handed body. So basically, there are simplest one which corresponds to object one. It's just solid torus. Then you have two solid torus, you glue them together, you have a genus 2 handle body, and so on, you proceed. So again, the pictures are very similar to the one. So you start with your four-dimensional handle body. You take it, picture. Okay. So this is now, it looks very similar, but now this is a solid picture. And now you multiply it times an interval. So this is a four-dimensional cube here. You can again remove some tubes out there. So if you have morphism, so for the moment it's a morphism from 1 to 2, what I'm drawing. And now you're using this front side of this handle body to draw the attaching maps for one and two. So it's very hard to draw it in really like this. So you see even less than you have seen in 3D case. But actually, so this morphism you can always think about them like this. So this is actually identity morphism in this category. So this is a Kirby diagram. So you can present like this the morphism from 1 to 1. And this is just the identity morphism. Okay, but you perhaps, so you would like to glue them together. So you can have morphism from some, so for example, this would be something like multiplication from 1 to 2.
What are the dots on the components?
It's for one handle. It's a Kirby diagram, the dots are one handle. So basically what we showed in the paper is that you can represent this for what we call 4KT, which are four-dimensional tangles. 4 it's just states because you can have also tangles to represent as three-handed bodies. So this is just for that you.
No, just going back, the condition for Habiro half-adroit, did you really mean the arrow on the right going down? I'm not understanding at all.
Yeah, yeah.
Oh, okay, sure.
So
Yes, you have.
thank you. Thank you. So it should be the one which makes sense, yeah? Okay. Okay, so then, for example, here you can have another one handle, then you can have some knot here, and then it ends usually with the same picture, with this identity morphism. So they all ends like this. And this would be morphism from 1 to 2. So this is a way how you use Kirby diagrams, which are just basically the attachings. You draw the attaching of 1 and 2 handles, but you don't. It's not a closed diagram because it doesn't represent a closed 4-dimensional manifold, but it represents a morphism in this 4HB. From some 3-dimensional one-handed body to some other 3-dimensional one-handed body. And so there is a complete diagrammatic calculus for this, and there are also morphisms which correspond to all the structures in the BP Hopf algebra, which I think are given on this exactly. So you see this at the end. So the last set of pictures, these are the pictures which represent, in terms of Kirby tangles, they represent the structure morphism of BP Hopf algebra: multiplication, co-multiplication, antipode, co-pairing, and everything else. Okay. So, and now we are coming to the point. So why is it interesting? So why should we care about this? And so you may care about this because of the following. So these 4-dimensional handle bodies which we consider in this category, so they are not considered up to diffeomorphism. So perhaps you know that to relate two such Kirby diagram, so the two such diagram are diffeomorphic if you can pass from one diagram to the other by handle slides and stabilization. And stabilization, these are moves which are remove and add a pair, cancelling pair of A and I, so I and I plus first handles. And the handle slides, it's a sliding of I-dimensional handles over I-dimensional handles for all I which you have in your settings. Yeah. So our setting is not, so the setting of this BP Hopf algebras is not appropriate to study things up to diffeomorphism, but it's appropriate to study things about two deformations. So who are two deformations? These are, they are generated by, again, the same handle slides. So again, I, and this I, because I have only 1 and 2 handles, it's again a handle slice of 1 handle over 1 handle, so 2 handles over 2 handles, nothing else. And then the stabilization, it would be only 1-2 stabilizations. Because, so I don't know how to add 3 handles to my picture. I'm working with 4-dimensional 2-handle bodies. I don't have 3 handles, so I do not consider 2-3 stabilization, which you need to accomplish this set to the old set of diffeomorphisms. And so this is a new equivalence relation. It's not a new equivalence relation, but it's not what people usually construct invariant up to. So usually they consider things up to diffeomorphisms. And so this is what I wanted to motivate. So why? So which kind of problem you can study in this setting. And so the famous set of problems in the setting is related to the called Andrew-Curtis conjecture. And this conjecture has 4-dimensional and 2-dimensional incarnations. So I will start now with the 4-dimensional one. And so this four-dimensional Andrew Curtis conjecture, I would ask for the following. So assume we have two four-dimensional heavy bodies. Or two four-dimensional CW complexes, so whatever. So that are diffeomorphic, then there are also two equivalents. So two equivalences means, so this is equivalence relation given by these two deformations. So clearly any two deformation correspond to diffeomorphism, so what is less clear, so clearly it's a more restrictive set of moves where there are any deformation, any diffeomorphism can be generated by a set of these two equivalences. So this is this equation, so in particular, so you can simplify it by saying, so assume that you have two handle bodies which are diffeomorphic to a D4, just a four-dimensional disk. Other two equivalences would be an equivalent of Poincare conjecture in this setting. And
No, sorry. Can I just, I would call this Gompf's conjecture because I think it's due to Gompf.
I think Gompf.
It's lifting of the Andrews Curtius from two complexes, because Andrews Curtius is.
So we can spend time. So to my knowledge, Gompf strongly conjectured the opposite. So Gompf conjectured that this is not the case, and
exactly,
and he even
exactly.
And what I'm formulating, it's something which is commonly thought to be false. But this is really exactly just lifting of the IC. So we have, and in generalized in the sense, it's not just related to the disks. It's related just to. So Gompf, so he even produced counterexample to this, and suggested the potential counterexamples here. So there is no known counterexample so far. And what I wanted to present now is a setting to work with the actual, so perhaps let me, when I'm speaking about generalized AC conjecture, let me also speak about actual AC conjecture. And the actual AC conjecture is about presentation of trivial group and so assume you have a trivial group which you give by generators and relations. And if you have the same number of relations as generators, you speak about balanced representation of the trivial group. And now you have a different balanced representation of the trivial group, which has the same number of generators and the same number of relations, but relations are different. Then what this conjecture says is that you can pass from one to another by the sequence of so-called AC moves. And these AC moves, so the three of them is you replace the relator by conjugation of this relator by any word in the tree group and your generators. You replace your relator by product of two relators, or you inverse your relator. There are actually, so this is what calls sometimes in some book by Nestler Q. Q transformations, and there is one more Q star. Then you replace your relator by its image under any automorphism of this free group. And there is another thing where you, which I will start, so that we call QQ star relation, where you are allowed to add one more generator and one more relation, which is a trivial relation, which just says that you can cancel these guys. But you still stay balanced. So you for example, if you get here just x1 is equal to r1 is equal to x1, you're not allowed to cancel them a priori, except you're working in this Q star setting where you can add or remove such things. Okay, so this is a conjecture. The conjecture, again, all people think it's completely, so it's wrong. There are a set of counterexamples, so let me perhaps give you an easiest, so potential counterexample is the following group. So you have just two generators and two relations. X to the power n is equal to y to the power n plus 1, and you have a braiding relation on x's and y's. And starting from n3 or bigger, it's unknown whether, so this is a trivial group, this is a representation of trivial groups, this is unknown whether you can pass from here to the trivial presentation by just this AC or ICQ or ICQ star double star moves. So if you can answer this question, so this is why I think it's important, then I think Thomson, Charlemagne, and Gompf proved that you will have a counterexample to Riemann-Slice conjecture and to the generalized property R. It's about, so if you get, it's about surgery on a link which produce some connected sum of its 2 times its 1s, and then the link should be basically just a trivial link. So there is a lot of topology which is behind of this thing, and so I wanted to finish this talk by emphasizing one more, so another work of Velina about this Andrew-Cart's conjecture in relation to this BP-Hopf algebra. And actually, so the BP-Hopf algebra, it turns out this is also a right setting to study this Andrew-Cartes, and not just thickening of the CW complexes, but also the CW complexes themselves. And so this is the following result. So this is the theorem of Velina. Which tells that, so you can organize the CW complexes in a category, which I'll call category of 2-dimensional CW complexes. So in this category, you will have only connected CW complex. You will always have just one zero cell. Then the object, it will be a number of the one cell attached to the zero cells. And then the morphism would be 2 cells attached to this one cells. And you can you can make this category to be equivalent to the category of group presentation, which looks like this. So perhaps just to give you one small idea. So the identity here looks like this. You draw it in this way. So this is identity. So it's attaching one cell to the word, which is perhaps AB minus 1. And so you draw it like this, and you squeezing this thing here just to one point, and then you're on that side. And so in terms of group presentation, it would be a presentation which starts with A, goes to B, and the relation is AB minus 1. Okay, so you basically, you can make equivalence between these two CW complexes and presentation of groups. And this is, on the other hand, equivalent to something completely algebraic, which we call 2-alg. And 2-alg, it's a symmetric monoidal category. Generated by a co-commutative unimodular Hopf algebra. So this makes the picture which I wanted to present you, and which is on the first page of my handout. Looking as follows. So if you have four-dimensional two handle bodies, which are basically generated by BP Hopf algebras, or algebraically described by this category 4-alg, you can take a boundary function, just take a boundary of this guy, and you will land in the category of three-dimensional cobordism with this boundary structure. You have a quotient functor from here to the 3-alg, generated by Habiro algebra just by taking a factorizable quotient. Again, here is the equivalent. Then, on the other hand, you can take here a fundamental group of your four-dimensional handle body, and you will come in the category of the relative presentation of the groups, which is equivalent to the 2-alg. And this 2-alg is again a quotient of the BP Hopf algebra. And as you see, this is a symmetric monoidal category, meaning that the braiding here goes to the, it becomes symmetric on these things, and you eliminate the ribbon morphism. It becomes identity, so it becomes trivial here. And the co-pairing becomes also trivial, just two copies of the identity. And so this is a quotient, and you see, so this looks as something extremely simple, this 2-alg generated just by co-commutative Hopf algebra, but this is actually the most complicated thing to study. And so our strategy is try to study this four-dimensional thickening to say something about this two-dimensional work. So thank you very much.
I'm a little confused. This counterexample is to the Hopf conjecture. This is the counterexample of what?
So this is assume assume that for n bigger than 3, it's impossible to reduce this presentation to a trivial presentation by using just the IC moves, but it's open.
Did he ask the Gomp conjecture?
No, he asked about this counterexample, which.
The potential counterexample.
Sorry?
Potential counterexample.
Exactly. Potential. Yeah. It's very, very important. Potential.
But, yeah. Because also Gomp gives the handle body structure of a lifting of this presentation. No? So it actually also gives a handle body which is potentially not too equivalent to before. So on both sides there is no.
You said that with the BP Hopf algebras, some common Hopf algebras like quantum groups are examples of those. In like UQSL2 or something, what do your new things look like? Like integral, and is the ribbon just the ribbon?
Thank you very much. Very good question. So you know that all quantum group produce ribbon categories. Most of them are already modular. So most of them are factorizable. So they are coming from quantum double. And there are some special cases. So for example, QSL2 is a case where R, so the root of unity, it's of like 0 mod 4, something like this. Then it's not factorizable. So it has some Yuga center, the representation category. But the problem is it's a very close to be factorizable. So basically, so this is what we also investigate with Marco De Renci. So that it's enough to add few topological more structure, like some cohomology class of spin structure in the manifold, and then so it will be graded just by this, and you see, yeah. So basically, you will introduce kind of grading. You will take. And you then you can prove similar theories that it's detect the boundary plus the structure.
Mm-hmm.
So therefore we are not so optimistic with quantum groups. And so I had a PhD student who is not here, who is studying what they call strongly not factorizable. So this is basically where this morphism is not. This morphism is definitely not equal to the co-integral, but it's just equal to 0.
Right.
And so they have also a list of these guys, so they have a lot of examples produced, so interesting papers. So this is by Manco and Fess, but unfortunately not yet logically interesting.
Okay. Thank you.
Let's thank Andrew.